This is the general nature of the riser in the 2,350 metres water depth site for buoy 4 in the Mediterranean off Cyprus. The buoy up here is being dragged by a combination of wind, wave, current forces, and we're interested in this part of our presentation in an area of the riser here which surprisingly sees some compression, and an area of the riser here just before the green buoyed area. This is football floats in this area. We're going to home in on these two areas. Worm in a hole. This diagram shows a riser that goes from point A, bare riser section, down to a section with floats. It's a long riser and extends beyond this picture. If the top end is moved downwards from point A to point B, the floats will move a little in this case, but point C will move a relatively long distance statically towards point D. However, dynamically the drag force is large, relatively large, going from C to D. So point C would more easily slip in this direction towards the riser with floats, like a worm in a hole. The bare riser has very little drag axially, but the float sections have relatively large drag axially, so they don't want to slip so easily like a worm in a hole, and hence this is a point at the place where the bare riser enters the riser with floats section where compression tends to occur. Of course, if this section from A down to the floats is long, you can get compression also occurring in the middle of the section. Now we're going to look at the compression and how it manifests itself as buckling waves in a 100-year storm with a John Swap spectrum gamma equals 2.5. Significant wave height is 29.3 feet. TZ, the zero crossing period, is a control number put in as 8.54, and the gamma for the spectrum is specified as 2.5 in what OrcaFlex calls a partially specified spectrum, resulting in a peak period of 11.24 feet. The frequency spectrum we can quickly look at is like this, described elsewhere. Here we're looking at a simulation replay. It's a minimum fuel case, the 1 knot current, a 1-year storm with significant wave height 29 feet, John Swap spectrum gamma equals 2.5, a 44 knot wind, and this is a special model made up with very fine resolution. In this box here we're looking at a point roughly 2,000 feet from the buoy down the bare riser section, and we can see during this selected piece of replay a buckle wave manifesting itself here as we get compression, a small amount of compression in this upper bare section. Down here we can see the point where the green indicates the floated section begins and the bare section on upwards to the buoy. The bare section is trying to slide down like a worm in a hole, meets the floated section, which offers significant axial resistance to sliding in this direction, and we see a very prominent buckle wave or compression wave forming. We're going to focus here on the riser tension at a location about 1,000 feet from the buoy. We see the timeline along here. This is in seconds from 0 to 120, and we're just replaying 2.5 seconds going from 97.5 to 100, where we know there is a 0 to negative tension occurring. And that's what we're seeing in the location where the riser meets the floats in particular. The plot here is the minimum tension along the length of the riser from the buoy at 0 down to a distance of 4,000 feet. During this simulation period, this plots the maximum negative tension or maximum compression that's seen during this section of the simulation. We're still in the same simulation, and we're looking at this 2.5 seconds of replay. And in this graph, which shows the arc length from 2,000 feet from the buoy to 4,000 feet from the buoy, we're looking at curvature. We're seeing a peak curvature of about 0.26. The reciprocal of that is the bend radius, which gets as short as the reciprocal of 0.26, which is 3.8 feet. And this location is where the bare riser meets the floated section, whereas this location, where we're also seeing a significant amount of curvature, is further up the riser at an arc length. We see 2,400 feet roughly to 2,500 feet, where we're getting the bend that we can see manifesting itself in this replay. See the bend forming now. This graph is showing us the effective tension instantaneously from the buoy down to an arc length of 5,000 feet. We see it's a very complicated pattern because we have, when we get to compression, going back to tension, we tend to get a shock wave, an axial stress wave going up the riser. It's difficult to make out, but it is occurring, which complicates the distribution of stresses in the riser significantly. We also tend to get reflection at the point where we meet the floats, which is at this arc length where we see this curvature. So we're getting a reflection both from this point and from the top end as a consequence of the dynamic behavior of the system. Now, I've noted that the riser makeup here in the OrcaFlex model was with very fine segmentation. The element lengths are about 2 feet, and these are much shorter than in our normal runs in this project. These runs take much longer to execute. And over here we see the typical segmentation that we used for most of the runs, where the element length is about 5 feet. And the behavior we see here is similar in nature, but now we need to quantify whether its magnitude is such that we're being misled, because there's not many elements that make up these bends, whereas in this picture we see there's quite a few elements that's making up each of these bends in the wave shapes. So these are identical simulations in that their input is waves, wind, current, the riser makeup, etc. The only difference is that we've got coarser segmentation in our typical production runs, than we have in this special case where we're looking at the possibility of over or underestimating the compression. So this graph is our graph of riser effective tension, and here we see the maximum compression with our course segmentation model, and we see that the negative maximum is around 1.6. Now I've shifted the screen over so that we can see the comparable graph of compression or negative tension, and we see it reaches a negative maximum of 1.4 compared to the negative 1.6 we had with the coarser model. So in this case, our finer model is showing us a more realistic but slightly lower compression than we had in the coarse model. The coarse model can be concluded as being conservative in its estimation of maximum compression values. Conversely, we see that our curvature with our fine model peaks at about 0.26, whereas in the coarser model it's peaking at around about 0.19. Therefore, this curvature in the coarser model is slightly non-conservative and would predict slightly larger values for the minimum bend radii resulting from the curvature. The reciprocal of the curvature is the bend radius. So the finer model here is giving us a slightly lower bend radius at any point in these compression wave situations.